thinking about space, matter, and time. But our quantum mechanics changed our conception of matter. Okay, first of all, what is quantum mechanics? All physical objects exhibit both particle and wave nature. So Werner Heisenberg and Erwin Schrödinger done a wonderful job on this. So we can see one by one. Before that, we know, according to classical theory, particle and wave are different thing. But after the invention of quantum mechanics, after the notable works of quantum mechanics, we can identify both particle and wave nature of light. So here, physical object described by a mathematical function called the wave function psi. It is a unique operator used in quantum mechanics. Here, experiment results are having 100% accuracy with theoretical results. But in classical mechanics, it's not up to the mark. Theoretical results are not in good agreement with the practical results. Then, in classical and quantum, what is the main difference? Actually, the inefficiency of classical theory is rectified by our quantum theory. In previous years, that is previous to 1900, classical theory successfully explained behaviors of macroscopically and microscopically visible particles only. But classical theory failed to explain the same for invisible and tiny particles like electron. After the invention of scopes, quantum theory successfully explained the following things. Actually, it explained the smallest discrete units of things like energy and matter. Specifically, classical theory fails to explain stability of atom, hydrogen spectral lines, and emission of light. These three things are not explained by classical theory. Also, in addition to them, some of the physical phenomena not explained, such as Compton effect, Zeeman effect, photoelectric effect, black body radiations. These 7 things are the basics of quantum theory. These 7 things excellently explained by our quantum theory. These limitations of classical theory rectified by our quantum theory. Right. So, with the contributions of Max Planck's proposal of quantum theory of radiation, BBR, black body radiation, in 1900, Albert Einstein's explanation of photoelectric effect with photons, and Niels Bohr's model of hydrogen atom, ultimately establishing principles like wave particle duality. So dual nature explained by our quantum theory. Simply we can say quantum plus mechanics. Quantum means simply saying quantity or amount. And mechanics, we can say easily motion of the body. So quantum mechanics explains motion of smallest possible discrete units. So this quantum mechanics deals with the invisible matter also, right? Quantum mechanics deals with the behavior of particles like electrons, protons, and neutrons and photons. Energy and matter are quantized and behave as both particles and waves. We can clearly see here in orbit, we know the electrons are spinning, also revolving. They are revolving the nucleus. Nucleus comprises of proton and neutron, we know. So the center core is nucleus. That center core nucleus is surrounded by electrons in various orbits. These things are explained clearly with the support of quantum mechanics. We can say easily about their charge, their mass, for proton, neutron, and electron, right? So we are giving symbol for proton P, for electron E, for neutron N, and we can say their charge. Electron is negatively charged, proton is positively charged, neutron neutral. There is no charge for neutron. So its location we can see in center core nucleus. We are having proton and neutron. Electrons are in the external orbits in various levels, various energy levels. Electron is spinning itself like our Earth, also rotating in the respective orbits, which is centered by our nucleus, comprises of proton and neutron. Right. So simply saying, quantum mechanics explains the behavior of matter and energy at the atomic and subatomic scales, that is invisible, right? Where classical physics failed. Okay. So now we are seeing subatomic scale to measure the size of particles smaller than atom. The size of the atom we know, 10 to the power of minus 10 meters, and it is whole. Atom comprises of nucleus and various orbits. In orbits, electrons, right? Nucleus is a central core of the atom. That nucleus is about 10 to the power of minus 14 meters. Below that, in the sense, inside the nucleus, we are having protons and neutrons. So their size is less than the size of the nucleus. Below that range, we are having quarks. Quarks are in between 10 to the power of minus 16 and 10 to the power of minus 17 meters. Okay, these are all some more examples for quarks and subatomic mass. We can see clearly the relationship between atoms, proton, neutron, that is nucleons, and quarks, right? We can say 10 to the power of minus 10 size in atom, then 10 to the power of minus 14 for nucleus, for proton 10 to the power of minus 15, for electrons 10 to the power of minus 18. In this picture, we can understand the actual mass of electron, proton, and neutron. When we are comparing the mass of electron, proton, and neutron, here we can say electron is having tiny mass when we are comparing with the neutron and proton. The electron is with negative charge and located around the nucleus. Neutron and proton most probably having same mass. There is a difference in point. For proton 1.676, for neutron 1.674. So the difference is in point, not 2 only. So both of them are having most probably same mass. And we can say neutron and proton also having large mass. Both of them are located in nucleus. Then just we can go through with the atoms. Atom is a basic building block of a matter. It consists of nucleus at its center core. Nucleus is having protons and neutrons. We know that nucleus is surrounded by electrons in various energy levels according to the energy they possess. Atoms can combine to form chemical compounds through chemical bonds. They are classified in the periodic table based on their atomic number, which is the number of protons in their nucleus. Atoms can form in various ways, including during Big Bang and through nuclear fusion in stars. Here we are seeing atoms and molecules, right? So collectively we can say atom is comprises of central nucleus along with the electrons in various orbits. Then molecules, compounds, ionic compounds, and we are seeing covalent bond also. Okay, we'll discuss about molecule. Molecule is a group of two or more atoms bonded together, forming the smallest unit of chemical compound that retains its chemical properties. There are two different molecules. One is homonuclear, the other one is heteronuclear. In homonuclear, it consists of atoms of one element like O2, O and O. But in heteronuclear, we can take the example of H2O, two hydrogens and one oxygen. So it composed of different elements. They are held together by chemical bonds such as covalent bond, where atoms share mutually electrons. Okay, so we are seeing the examples of molecule, oxygen and nitrogen. Both of them are the examples for homonuclear, and for heteronuclear we are having ozone, methane, ammonia, glucose and caffeine. Right, now we may discuss about ions. Atoms are molecules that carry on electrical charge due to the loss or gain of electrons. They can form the bondage by losing or gaining electrons, we know. There are two main types of ions. One is cation, another one is anions, we know. Cation is positively charged, anion is negatively charged. So positively charged ions, they have lost one or more electrons. Anions, they gained one or more electrons. Ions also can be monoatomic, consisting of single atom, or polyatomic, consisting of two or more atoms. Okay, so now we are seeing example for ions and how the ionic bonds takes place. We are seeing the example of sodium chloride atom. So the electron in the outermost orbit of sodium is given to chlorine atom. That chlorine atom is getting the sodium atom. So both of them are forming the bond. As a result of it, we are getting sodium chloride. Okay. Now we may see about element. Yep. Element is a part of compound or complex whole, often implying irreducible simplicity. Right. A pure substance consisting of atoms with the same number of protons. There are 180 known elements, each represented on the periodic table. So now we are seeing the elements organized in periodic table. So the 18th column is noble gases, 17th one is lanthanides, 16th we are seeing different groups, right? So we are seeing metalloids, non-metals, halogens, then transition, post-transition, alkaline earth metals, alkali metals, radioactive materials. We are seeing different types of material organized in a systematic manner in periodic table. Periodic table is the basic one for all our researchers. There is a more space to do or to continue our research in physics and chemistry field. Okay. Now we are seeing different atomic models. Early 20th century, Rutherford and Bohr revealed the internal structure of atom and simplifies earlier models and make easy to understand quantum mechanics. So both of them came with their own atom models in 1911 and 1913. Okay, the first one is Bohr atom model, that is 1913. In H atom, spectrum energies are restricted to certain discrete values. Electron is restricted to well-defined circular orbits labeled by quantum number n. Energy absorbed in discrete amounts, that is quanta, we can say photons, corresponding to differences between these restricted values. The change in energy is energy level 1 difference energy level 2. Otherwise we can say energy level 2 difference energy level 1. So totally energy is called as E is equal to h nu. We know the formula, right? Here we are seeing one nucleus and energy level, two different energy levels. So the atoms are usually in ground states, that is energy level 1. Whenever they are absorbing the energy from external stimulant like photon. So h nu here represented by a photon. So a photon is falling on this electron. The electron is getting the energy from photon and uh, gaining the energy. That electron is moving to higher energy level, that is E2, from energy level 1 to energy level 2, ground state to excited state, by absorbing the external energy given by the photon. So this is called the absorption process. If the electron is in higher energy level, that higher energy level or excited state is highly unstable. So the electrons in the higher energy level try to fall immediately from higher energy level to lower energy level. At that time, they may leave the excess energy, because energy level 1 is having certain amount of energy and energy level 2 is having certain amount of energy. Whatever energy they are having is arranged in the respective energy level. So if the electron in ground state is gaining excess energy, they can move towards their respective energy, that higher energy level. If the electron is in higher energy level, we told already, higher energy level is highly unstable state. So from the highly unstable state, the electron try to fall and towards the ground state. At that time, they may liberate, they may release the excess energy is having. So that is also released in the form of photons. Okay. Atomic and molecular spectroscopy is giving us more and more information. Actually, this one is not explained by our classical mechanics or classical physics. Here, the quantum theory is explaining excellently about the hydrogen spectra. We know, we studied in schools, Lyman, Balmer, Paschen, Brackett, and Fund series. These are all explained by our quantum theory. So it's also the success of quantum theory. 17th, we mentioned, so it is also one of the success. Then Max Planck's energy quanta. We are introducing the word quanta right here. We know the energy is not a continuous one, but it is emitted and absorbed in discrete packets as quanta. But we are seeing, we are getting the light from our tube light or LED bulbs. That is, we are thinking it's a continuous one, right? But it is continuously coming in discrete manners, right? It is coming out packet and packet of light energy from the light source continuously. So the continuous process of coming out light is showing us it's a continuous process, but it is a quanta, discrete packets, right? So packet and packets of energy is coming out with some very minute time delay, so that this very minute time delay is showing us it's a continuous process. Okay. Einstein's photoelectric effect, it's also not explained by classical theory, it's explained by our quantum theory. In 1905, Einstein applied Planck's concept to light. That is, light is made of discrete energy particle called photons. So it's also the success of quantum theory, but failure of classical theory, right? Okay, so we can say easily, we can understand easily using those figures. First one, we are seeing absorption process. Whenever light is falling on the ground state electron is absorbing the energy and reaching the higher energy level. And then when it is coming back to ground state, the energy is liberated spontaneously. It's called a spontaneous emission. When the electron in higher energy level is stimulated to emit, right? Spontaneous emission is the electron is automatically coming down, liberating or releasing the energy. That is spontaneous emission. If one external stimulant is given to that excited state electron to release more amount of energy, that is stimulated emission. This stimulated emission is used in our laser. So we know different types of laser: solid state laser, gas laser, semiconductors laser. These are all working under this principle only. So there is a concept, band gap, E is equal to h nu. We are telling that h nu is the energy of band gap. Band gap is nothing. We know the value of energy level 1 and energy level 2. The difference between these two energy level is called band gap, right? So the energy absorbed by the electron must be greater than the energy of band gap. So it is having the energy greater than the band gap, then only the ground state electron can move to excited state, right? Okay. Photon and its property. We can discuss about photon. The term photon was coined by Gilbert Lewis in 1926. Photon is an elementary particle that constitutes EM radiation, including visible light. It is a particle without mass. We have to underline the word particle without mass and without electric charge, right? But it carries energy and momentum. Without mass, without electric charge, it carries energy and momentum. Photon is exhibiting dual nature. It acts as a wave as well as particle. Photon is exhibiting dual nature. It acts as a wave as well as particle. We can see some examples for wave nature as well as particle nature. They are discrete energy values emitted as small packets or bundles or quantas by the source. Discrete in the sense it is not coming continuously. It's emitted as packets or bundles, right? Continuously the bundle of light energy is coming out of the source. They possess definite frequency or wavelength. We can see what is frequency and what is wavelength. According to Planck, the exchange of energy between light and matter is not a continuous one, but it is in the form of packets or quanta of definite energy proportional to frequency of light, right? So E is directly proportional to nu. H is Planck's constant, so we can say easily E is equal to h nu, where the packets of energy h nu is called photon. Here we are seeing photoelectric effect. Whenever the light energy is falling on cathode beyond its threshold level, the light energy can be absorbed by the electrons in the cathode, and the electrons in the cathode are gaining the energy by the incident light, and they are moving towards anode. They are starting their journey towards anode. They are collected by anodes. They are creating running of electrons. We know simply the flow of electron is current, right? So the photoelectric effect is when photons are falling on cathode, the flow of electrons started. Photoelectric effect. Electricity induced by photons. So photoelectric effect is whenever the light is incident on some photosensitive metal. The photosensitive metal is absorbing the incident light particularly the electrons in the photosensitive metal. They starts its journey, they starts moving. So the photoelectrons are starts moving, gaining the energy from incident light. Okay, so we can say here, for photoelectric effect, the frequency or the wavelength is very much important. You can see here for the wavelength of red, that is wavelength of red is 700 nanometer, that is possessing 1.77 electron volt. There is no ejection of electrons. But for 618 nanometers, that is for 2.01 electron volt, there is a ejection of very few electrons. But for blue wavelength of 400 nanometers, we are getting more and more amount of electrons. Electrons are coming out like anything. So its energy is 3.10 electron volts. We are not getting electrons from photosensitive material for red wavelength, but we are getting more amount of electrons from this photosensitive material by blue wavelength. Here the wavelength is low for blue, but its frequency is high, right? The frequency of blue is high, but its wavelength is low. But in the case of red, wavelength is high, but its frequency is very low. We can see what is wavelength, what is frequency. Here we are seeing what is photoelectric effect. Here we are seeing the picture of Einstein, right? With good smile. When a photon strikes a metal, it transfers its energy to an electron. When photon strikes a metal, transfers its energy to an electron. If this energy exceeds the metal's work function, that is, work function is phi. We are giving this phi in below formula. K is equal to h nu minus phi. When the energy exceeds the metal's work function is minimum energy to eject an electron. The electron is emitted with kinetic energy. So a photon strikes the metal, that photon absorbed by electron as energy. Then whenever the energy exceeds work function of metal, electron is emitted with kinetic energy. So we can say, we can explain with the simple formula K is equal to h nu minus phi. Phi is work function of that metal. Then we can see here a bucket of metal, right? Whenever light is falling on this metal, the photon is giving its energy to the electrons in the bucket. When it is receiving photon, immediately that energy transferred to that electrons. So whenever the electrons are gaining excess energy, they are starts moving from its place, right? So we can explain metal is a bucket of electrons. They need some energy in order to jump out of the bucket. That energy is supplied by the light photon. Light can supply this energy. The energy from light, that is photon, transferred to the electrons. So energy transferred from light to electrons. Electron uses some of the energy to break out of bucket. Remainder appears as energy of motion, that is kinetic energy. Here also we are giving del E is equal to E2 minus E1, that is h nu, right? Okay. So here we are seeing whenever the photon is falling, the electrons comes out, right? Can you see legibly? Green color arrow mark is light. So that light is falling, and then The electron is gaining the light energy and eject out from the bucket. So here also we are seeing ground state electron, excited state, it's moving by absorbing the external energy from photon. Then we know the excited state is highly unstable, so it is releasing the photon to reach the ground state. Okay, now we are seeing the spectrum, right? Until the light wavelength passes a certain threshold, no electrons are ejected. See, for red color beam, there is no threshold because it is having very high wavelength, but it is having very low frequency, so that no electrons are ejected from this process, this red color wavelength. So for long wavelength, low frequency; for short wavelength, high frequency. For high frequency, electrons are ejected. For example, for violet, blue, we can eject electrons from a bucket. So high energy photons, low energy photons. These long wavelength colors are called, the photons are called low energy photons. But high energy photons are short wavelength and with high frequency. They can able to eject the electrons, but long wavelength with low frequency cannot eject electrons. Okay, so here we are seeing very good example for the wavelength, high wavelength and low wavelength. For low wavelength, the electrons are, photoelectrons are ejected from the photosensitive metal. But for high wavelength, low frequency, we can't able to eject the electron from photosensitive metal. Okay, so what is behind that? Simply we can say number of photons per second. Number of photons per second. Okay, for short wavelength and high frequency, number of photons per second is the reason behind that. Okay, so power divided by energy per photon. Okay, so here in the sum we are seeing a red and green laser or produce light at a power level of 2.5 milliwatt. Which one produces more photons per second? We can say simply green, because red is having very high frequency, sorry, very high wavelength but low frequency, but green is having short wavelength but very high frequency, so it can produce more photons. Green can produce more photon than red. When we are comparing green with red, green is producing more photons per second. See, again we are telling the same thing. There is a radiation by a photon. That photon is inducing one electron. Einstein said that light is made up of photons, individual particles, each with energy hf or h nu. That is indicating, nu or f is indicating frequency. One photon collides with one electron, knocks out of the metal. Like in carom board, right? Striker is striking the coin and packeting. Likewise, here the photon collides with one electron, knocks it out of metal. If photon doesn't have enough energy, if striker is not having that much energy, required energy, it cannot knock the coin. So if photon doesn't have enough energy, it cannot knock out the electron. Okay, so that is because of low frequency, high frequency concept, right? If it is having high frequency, it can eject out the electron. So intensity is number of photons per second. If more number of photons are coming out per second, that is having very good intensity. right? Okay, so minimum frequency, maximum wavelength required to eject electron. As a conclusion of this discussion, we are telling minimum frequency, maximum wavelength required to eject electron. But our actual case is the photon which is having maximum frequency but with minimum wavelength, right? So we must understand that concept. Okay, so as a conclusion we can say uh, red light is low frequency, so that is having low energy. Violet is having high frequency, so it is having high energy. So red light will not eject electron from metal. So no matter how intense, single photon energy h nu or hf is too low, as in ultraviolet ray, right? Okay, so we can understand some of the terms used for this photoelectric effect. A is amplitude, lambda is for wavelength, and nu is frequency. We can say C is equal to nu lambda, and we can say nu is equal to C by lambda, right? Wave number, we can say 1 by lambda. C, velocity of light in vacuum, that is indicated by C. Here we are seeing the entire spectrum. In the entire spectrum, we are seeing visible is in between 700 nanometer and 420 nanometers. Beyond this, we are having near infrared, far infrared, and microwave, then finally radio waves. Below the visible range, we are seeing ultraviolet, vacuum ultraviolet, X-rays, gamma rays, cosmic rays. You can imagine the safest zone is visible only. Beyond and below the visible range, we can't predict our happenings, right? And they are telling molecular rotation, molecular vibration, electronic excitation, core electron excitation, nuclear excitation. These are the different process takes place in our EM. EM means electromagnetic spectrum, right? Okay. Now we are seeing black body radiation. So black body, first we may know about the black body. What is a black body? Black body is a small holed ball like structure. It is blackened completely by lamp block. Most probably, we may take a copper ball with small hole, and we are blocking this copper ball with the help of lamp block. That is called black body. It can absorb all the radiations falling on it. Likewise, it can absorb radiations of all wavelength falling on it and emits back all the falling wavelength when it is heated, right? At particular temperature, it can re-emit all the wavelengths absorbed. When a radiation enters through the small hole, it's subjected to multiple reflections inside the hollow cavity until it is completely absorbed. So, black body is a small hole ball made up of copper and with the support of a lamp block, it is blackened, right? It absorbs all the radiations of wavelength falling on it, and it can re-emit all the wavelength when it is heated at particular temperature. Here we are seeing various temperature and along with wavelength, also the power of the thing. So this is black body radiation spectrum, BBR, black body radiation spectrum. So here we are seeing the extension of black body radiation spectrum, right? We are heating from 1250, 1500, 1750 up to 2000 K, right? We can see here from UV, ultraviolet, visible, up to infrared radiations. And in x-axis, we are having wavelength, and in y-axis, power, right? And in this, we are having the peaks according to the respective temperatures. The radiation emitted by a block body is called BBR, block body radiation. It is independent of size, shape, and material of the body wall. Block body radiation graph is obtained by plotting emissive power versus wavelength at constant temperatures. So we are having 4 different constant temperatures here. Simply saying, for increasing temperature, maximum radiator power is observed for the minimum wavelength, right? We can say here, for minimum wavelength, maximum radiated power is observed. For increasing wavelength, that is lambda maximum, even though the temperature is high, power is decreasing. We can see this concept easily in this BBR, black body radiation spectrum. For lambda maximum, even though the temperature is high, power is decreasing. That is block body radiation. To explain block body radiation, we are having Kirchhoff's law of radiation, Stephen-Boltzmann law, fourth power law, we can say simply Stephen-Boltzmann law, right? And then Wien's displacement law, Rayleigh-Jeans law. These 4 different laws are supporting BBR, block body radiation. Wien's displacement law is mathematically explained as lambda maximum into T, that is product of lambda maximum and T is a constant, right? Rayleigh-Jeans law is giving the energy distribution is directly proportional to the absolute temperature and inversely proportional to the 4th power of its wavelength, right? So the classical theory fails to explain block body radiation, so that Planck used quantum theory to explain block body radiation. These 4 laws are supporting quantum theory. In Wien's displacement law is good for shorter wavelength only. Wien's law is used to determine temperature of stars depending on its colors, right? But Rayleigh-Jeans law is good for longer wavelength. See, Wien's displacement law is good for shorter wavelength, but Rayleigh-Jeans law is good for longer wavelength, right? Wien's displacement law and Rayleigh-Jeans law don't agree with their experimental results, right? In classical theory, but whenever we are approaching quantum mechanics with the support of quantum mechanics, they are having very good agreement and they are having very good accuracy with their practical values. That is, both theoretical and practical values are having good agreements. Now we are switching over to dual nature, right? Dual nature of light. That is matter waves, wave particle dualities. This concepts evolved in 1920s. According to classical mechanics or classical physics, the particles and waves are distinct. We can say particles characterized by position, mass, and velocity, but waves are characterized by its wavelength and frequency. Sometimes matter, classically particles, can behave like waves, and radiation, classically waves. Radiation, classically waves, can behave like particle. Matter behave like waves, radiation behave like particles. So quantum physics reveals light exhibit dual nature. It can behave as wave as well as particle. We can prove this dual nature of light by the following experiments, by interference and diffraction. So these 2 different phenomena, interference and diffractions, are confirming the wave nature of light, right? Likewise, particle nature explained by photoelectric effect and Compton effect. Photoelectric effect we discussed, and Compton effect we are going to discuss. So wave nature explained by the phenomena like interference and diffraction, right? Likewise, particle nature explained by photoelectric effect and Compton effect. So here we are seeing different waves with different frequencies. The first wave is having low frequency. Low frequency in the sense the waves per second is very minimum, but it is increased in the middle case, right? Okay. Then we can discuss about the fundamental things about wavelength and frequency. The distance between successive crests and trough of wave is wavelength. So the distance between successive crest and trough is called wavelength, right? Two tops, two bottoms. Here we are mentioned in the picture. And we can see the amplitude, the value of amplitude, the maximum distance reached both in positive and negative region, right? We are witnessing the wavelength, both crests, both in trough. Okay. Here lambda is equal to V by F. F is frequency. V is the speed of wave and F is its frequency. In the visible spectrum, red light has the longest wavelength. We know that violet light has the shortest, about 380 nanometer. Wavelength is a fundamental property of waves, including electromagnetic waves. These are all the things related to our wavelength. Now we are switching over to frequency. In this picture, we are seeing high frequency wave and low frequency wave. For a particular period of time, we are having high frequency wave. We are having more frequency in the first one, and in low frequency wave we are having very minimum waves. Okay, the number of occurrences of a repeating event per unit of time. In practical cases, we are using the word frequency when we are using the example of bus frequency. Frequently we can ask, what about the bus frequency in this area? How many buses may come? Is there continuous buses, continuous service of buses, frequent bus service, right? So likewise, both of them are having similar meaning. Number of waves that pass a fixed point in a given time period measured in hertz, right? Wavelength is measured in nanometer, meter, Angstrom unit, right? Here we are measuring the frequency in hertz. Frequency specifies the rate of oscillatory and vibratory phenomena such as sound and light. We can say frequency F is equal to 1 by T. T is time period, right? So F is equal to 1 by T. Time period is equal to duration of one cycle of the repeating event. Frequency and wavelength are fundamental thing used in quantum mechanics. I think you may get clear about wavelength and frequency. Okay, now we are switching over to our de Broglie concept. French physicist Louis de Broglie in 1924 suggested his views. Like light, material particle are also possess dual nature. According to de Broglie, a moving particle is associated with waves, right? So that is simply called as matter waves. The waves associated with material particle are called matter waves or de Broglie waves. The matter waves are simply material based on material particle like electron, proton, and neutron. We are having the formula for matter waves for wavelength. To mention the de Broglie wavelength, that is h by p, that is h by mv. Okay, we can see the properties of matter waves. Matter waves are not EM waves, that is electromagnetic waves. They can travel faster than velocity of light. Its smaller velocity is inversely proportional to its greater wavelength. So we know velocity and wavelength, both of them are inversely proportional. If any one of them is smaller, the other one is greater automatically. Its velocity is not constant and it depends on the velocity of material particle. If particle is lighter, then its wavelength is greater. Electrons have lowest mass. We know that they are not a physical quantity, but it is a wave of probability. We can say when wave becomes undetermined and particle becomes undetermined using the conditions. This condition is called as Heisenberg's uncertainty principle. Like photons, electrons, protons, neutrons, atoms, and even molecules have wave properties. As mass increases, wavelength decreases. We can remember C is equal to nu lambda, that formula. C is velocity or speed of light, and nu is frequency, lambda is wavelength of light. And we can say matter waves or Lewis de Broglie waves are explained by these properties. Wave particle duality is explained likewise. De Broglie wavelength, probability amplitude, independence from charge, propagation in vacuum, experimental validation, application in technology. Okay, then de Broglie wave equation, we can say and explain it simply. It is very important one also. So this concept evolved in 1924 from the dual nature of light. Total energy of a photon can be written in two ways. First one, we are considering as a wave of frequency nu. Its energy is given by E is equal to h nu, right? It is based on Planck's quantum theory. Based on Einstein's theory, considering a particle of mass m, its energy is given by E is equal to mc square, right? We are going to compare and equate both energies. To obtain momentum of photon, we are equating both the energies. E is equal to mc square and E is equal to h nu. So mc square is equal to h nu. And we can give 1c to the other side. So mc is equal to h nu by c. And we are introducing lambda because we know the value of lambda is c by nu, right? So nu by c is replaced by 1 by lambda here. So p is equal to h lambda. So that momentum is p is equal to mc. So lambda is equal to h by p. We can explain momentum p as h by lambda for proton. Right, for particle, P is equal to mv. So lambda is equal to h by mv. This lambda is equal to h by mv is de Broglie wave equation. We are going to see different values for mv, right? So we can see de Broglie wave equations for energy and others. The above relation is applicable to any material particles as well as photons. For a particle of mass m moving with velocity nu, momentum is given by p is equal to mv. So that is lambda is equal to h by mv. This is simply called as de Broglie wave equation. Okay, here we are seeing de Broglie waves in terms of energy. We know kinetic energy E is equal to half mv square and we are multiplying by m on both sides. So E becomes em and half mv square becomes half m square v square. Then we are taking the 2 from right hand side to left hand side. So 2em is equal to m square v square. We know de Broglie wavelength is lambda is equal to h by mv. So we are removing powers from m square and v square. So it becomes m and v. So the removed powers is given as square root in the opposite side, that is in the left side. So square root of 2em is mv. So the value of mv is square root of 2em. So we can replace that mv by square root of 2em. So the lambda is equal to h by square root of 2em. That is de Broglie waves in terms of energy. So de Broglie waves in terms of energy is lambda is equal to h by square root of 2em. Then now in terms of voltage, de Broglie waves in terms of voltage. Here we are starting with the same kinetic energy of mv square, but we are replacing E, that energy, by electron EV, right? Charge E and V. So E replaced by EV. As usual, we are multiplying by M on both sides. So EV becomes MEV, that is equal to M becomes M square. That is equal to MEV is equal to half M square V square. Then we are taking 2 from right hand side to left hand side. So it will become as 2 MEV is equal to M square V square. We are in the interest to get MV. So to get MV, we are removing the square in right hand side and adding this as a square root in left hand side. So MV is equal to square root of 2 MEV. So we can apply in de Broglie wavelength, that is lambda is equal to h by mv. So mv replaced by square root of 2 mev. So h by square root of 2 mev. So this is de Broglie waves in terms of voltage. So we discussed de Broglie waves in terms of energy as well as de Broglie wavelength in terms of voltage and energy. Okay, now we are going to see in terms of voltage. For this, we are taking 3 by 2 kBT. The difference between the above two cases and this one is we are taking the energy as 3 by 2 kBT. As usual, we are multiplying by m on both sides. So it becomes 3 by 2 m kBT half m square v square. And we are removing both 2's in both sides. So it will become 3m kBT and m square v square. We are interested only in mv to replace in de Broglie wavelength formula. So lambda is equal to h by mv. This mv is replaced by square root of 3m kBT. So de Broglie wavelength in terms of voltage is lambda is equal to h by square root of 3m kBT. Right. Then we are coming to wave function. It is a peculiar one in quantum mechanics. So wave function psi is explained here. A wave is representing the spatial distribution of a particle. Electrons in an atom are described by a wave function centered on the nucleus, right? Psi is a function of coordinates defining the position of classical particle. In one dimension, psi of x, but in two dimension, psi of x and y. In three dimension, psi of x, y and z. Okay, right. Psi may be time dependent. So we can explain as psi x, y, z and t, time dependent. Okay. Then here we are seeing Heisenberg's uncertainty principle. It is explained and evolved in 1927 by Heisenberg. What is it? It is impossible to specify simultaneously with precision. Precision means accuracy, both momentum and the position of the particle. So it is impossible to specify simultaneously both momentum and position of particle. Simply saying, we can't see both position of the particle and momentum. Position of the particle and momentum can't observed simultaneously is given by Heisenberg's uncertainty principle. Here we are seeing that formula dpx into dx greater than or equal to h by 4p. We can say h cross is h by 2 pi. So here we can replace with that. If we know the position exactly, we know nothing about momentum. If we know momentum exactly, we know nothing about position. That is explained by Heisenberg. Okay. So here we can see the pictorial representation for the momentum and the position of particle can't observe simultaneously. Okay, so we are switching over to Compton effect. This is the experimental setup of Compton effect. The source we are using here is X-ray tube. The X-rays are coming out of X-ray tube and they are streamlined with the help of two different collimators. The collimators are streamlining the X-rays coming out of the X-ray tube. With the help of these collimators, very thin beam of X-rays are falling on the analyzing crystal, right? So that is falling on the analyzing crystal that was diffracted to various angles. That diffracted rays are observed by photographic plates which is arranged surrounded by this crystal. Okay, so here we are observing the diffracted beams in various angles. What will be observed for theta is equal to 0, theta is equal to 45, theta is equal to 90, theta is equal to 135. We can observe in various angles. So we are using one ionization chamber here. 1923, Compton's full name is Arthur Holy Compton. He examined the behavior of X-rays scattered from a block of graphite. Graphite block is scattering this X-ray. He measured the wavelength of scattered X-rays at different scattering angles. Many of the scattered X-rays were found to have lower frequency. So this is called Compton scattering. Right, when a monochromatic beam of X-rays of wavelength is allowed to fall on carbon block, that is graphite, with low atomic number, scattered beam consists of X-rays of two components, two different components we are observing. One is with equal wavelength of incident wavelength and the another one is with a higher wavelength compared to the incident wavelength. So we are observing two different wavelengths. So there is a shift from incident wavelength. One is incident wavelength, another one is having higher wavelength when compared with incident wavelength. So the shift between the incident wavelength and the higher wavelength. So the shift is called as Compton shift. This phenomenon in which there is a change in wavelength of the scattered X-rays is called Compton shift. This phenomenon or this effect is called as Compton effect, right? Single wavelength is observed after scattering as two. One is same wavelength of incident and another one is slightly different from incident one. So there is a shift between the incident. That shift is called Compton shift. Here we are having theory of Compton effect, what we explained. Okay, so he is the gentleman who explained this effect, Arthur Holly Compton, right? He explained in the year of 1936, and the month is Jan. Okay, there is elastic collision between incident photon with the energy h nu and momentum h nu by c. It transfers some of its energy to the free electron on the carbon block. Due to this energy transfer, the electron acquires kinetic energy and recoils with the velocity v, making an angle phi with the direction of incident photon. The energy of recoils electron is mc square and momentum is mv. From the principle of conservation of energy, we know the principle of conservation of energy, right? Sum of the energy of photon and electron before collision, sum of the energy by photon and electron of the collision. To calculate the total energy before and after the collision. So the change in wavelength d lambda or del lambda is h into 1 minus cos theta divided by MOC. This is the final expression to mention Compton shift. Del lambda or d lambda informs us change in wavelength, right? That is d lambda or del lambda, shift in wavelength. That is explained by h, that is Planck's constant, into 1 minus cos theta divided by MOC. Right, we can say different special cases. If theta is equal to 0, theta is equal to 90, theta is equal to 180. For theta is equal to 0, cos 0, 1, we know. So there is no scattering. Scattering is absent. So no shift in wavelength. So change in wavelength, that is d lambda or del lambda, is 0. So there is no scattering. There is no shift in wavelength for theta is equal to 0. For cos 0, 1, we can't observe del lambda. But for theta is equal to 90 degree, we are applying this 90, cos 90 for 1 minus cos theta. So, as a result of this, we are getting lambda is equal to 0.0243 Armstrong. This is known as Compton wavelength. This 0.0243 Armstrong is Compton wavelength, which has a good agreement with experimental results. See, for theta is equal to 180, d lambda, the change in wavelength is 0.0484. For 90, 0.0243. For 180, 0.0484. Compare both of them. Okay, for 180, the shift in wavelength is found to be maximum. Compton shift, change in wavelength, depends on scattering angle only, depends on theta only. The wavelength of scattered X-rays become longer as the scattering angle increases. Compton shift is larger, del lambda is larger for the smaller rest mass of the scattered. So that we are selecting that material, carbon black, based on these things. Independent of wavelength of incident radiation, independent of nature of the material. See, experimental verification of Compton effect. Compton was the first to determine change in wavelength d lambda. Here, X-rays are used as source to scattered by a carbon block, that is graphite, right? Monochromatic X-rays from a molybdenum target falls on graphite, and they scattered through various angles. We are observing intensities of scattered X-rays at different angles. The experiment is repeated for various scattered angles, and the wavelengths of scattered X-rays are measured, observed clearly, keenly. At each angle, two peaks appeared. Wavelength of one peak doesn't change, and it is same as that of the incident X-ray, and it is called unmodified component. Another one is modified component. Wavelength of other peak varies strongly with the angle, so it is called modified component. So we are having two different things. One is modified, another one is unmodified. So the change in wavelength, change between the modified and unmodified, is called change in wavelength. That shift between the wavelength is d lambda or del lambda is called Compton shift. In figure, we are seeing for 0 degree, for theta 0, cos 0, we are having only one peak, that is, we are observing unmodified wavelength only. But for 45 degree, for 90 degree, for 135, we are having two distinct peaks, right? So because of these two different peaks, we are having difference in their wavelength. So change in wavelength is observed as change in wavelength, that is del lambda or d lambda. So this is called as Compton shift. Okay. So once again, we are seeing the experimental arrangement. So this circular table is mentioning about the camera can move, that is X-ray detector can move in this different angles, right? So here we are having graphite target, and we are having two different slits to make it a thin beam from the monochromatic X-ray source, right? Reason for Compton scattering not taking place for the visible light. Small difference in wavelengths between incident and scattered light is very hard to detect using visible light. We can't differentiate this thing in visible light with wavelengths of the order of 5000 into 10 to the power minus 10 meters. However, it is comparatively larger for X-rays, so that we are using X-ray source, which have wavelengths of the order of 1 Armstrong unit, right? That is 0.1 nanometer. So the X-rays were used to demonstrate that such scattering takes place. Okay. Why X-rays are used to study single crystals or different planes? X-rays are very high energetic radiations of very short wavelength, that is 1 Armstrong. So it can penetrate solids. The crystal planes are arranged with spacing of the same 1 Armstrong. So both of them are equal. The short wavelength of X-rays and the crystal spacing, both of them are equal. They are about 1 Armstrong. Due to this fact, X-rays get strongly diffracted from various crystal planes. By analyzing the diffraction pattern of a crystal, its internal atomic arrangement can be determined. Hence, W.H. Bragg explained the phenomenon of X-ray diffraction from a single crystal. Hence, this was the reason for using X-rays for the study of crystal structure. So, very short wavelength equivalent to the spacing between the crystal planes, that is 1 Armstrong. So that we are using X-rays to study single crystals. And one more components, G.P. Thomson's experiments. Here also we are using X-rays. Here, X-ray powder diffraction. In the previous case, crystal, right? So this is the experimental setup. We are having cathode, anode, and diffraction pattern recorded in photographic plate. We are maintaining vacuum with the support of a pump, and high tension battery we are using about 10,000 to 50,000 volts, right? This battery is connected between cathode and anode. Electron beam flows through anode A and then it is allowed to fall on slit. Slit we know making unidirectional. A fine beam is coming out of the slit. Accelerated fine beam is allowed to fall on thin film made up of gold or silver or aluminum in the order of 10 to the power of minus 6. The electron beam from the film is received by the photographic plate and it creates well-defined concentric rings about center spot. These patterns may get by developing the photographic plate. Nowadays we are using digital observation to avoid energy loss of electron by their collision with the gas molecules. The whole apparatus is exhausted to a high vacuum. This experiments done in vacuum. So these are all the things related to G.P. Thomson's experiment. Okay. So as a result of it, the wavelength depends only on the accelerating voltage and independent of material target. These wavelengths are in very good agreement with the wavelength obtained by de Broglie relation. This pattern is similar to X-ray patterns. This diffraction pattern can be disturbed by magnetic field because we are using magnetic field for focusing. It shows that the pattern was produced by electrons and not by any radiation. So the wavelength determined is associated with electrons. It is observed that the beam shifts correspondingly and the pattern is produced by electrons, could be by X-rays. X-ray pattern is not affected by electric and magnetic fields. Diffraction pattern can be produced by waves and not by the particles. So G.P. Thomson says that electrons behaves like waves. In this way, this experiment strongly proves the existence of matter waves. Now we are coming to Schrodinger's time-independent wave equation. It is also one of the masterpieces in quantum mechanics. In 1926, Erwin Schrödinger, an Austrian physicist, developed a wave equation to describe the dual nature of matter waves. It is one of the fundamental equations in quantum physics. He developed this wave equation by combining the de Broglie wavelength and classical wave equation. So this Schrödinger wave equation governs the variation of wave function in space as well as time. There are two different forms of Schrödinger wave equations. They are time dependent and independent Schrödinger wave equation. First, time dependent wave equation. For this, we have to consider a system of stationary wave associated with a moving particle. Psi be the wave function we know of the particle along x, y, and z coordinates, all the three coordinates. Axis at any time t, a particle can behave as a wave only under motion. So it should accelerated by a potential field. Therefore, the total energy E of the particle is equal to sum of its potential energy and kinetic energy. This Schrödinger wave equation applied to particle in one-dimensional box as well as two-dimensional box, also for three-dimensional potential box, right? If it is a case of one-dimensional box, its movement is restricted only in x-axis. Now we may consider a particle of mass m moving in one-dimensional box of infinite height with width L. We can take the example of a prison. Prison wall is having very high wall, the prison wall, right? One cannot climb over it easily. Here we are taking infinite height of wall with L. The particle is freely moving inside the box. The particle is confined between the length L of the box. The length L in the sense it can move only in x-axis, and it is having elastic collisions with intrinsic potential walls. Elastic collision means there is no wastage of energy. It can move back and forth elastically, right? Bouncing back and forth elastically without losing its energy. For a particle moving freely at the bottom of potential well, potential energy of the particle at the wall is infinite, right? Potential energy of the particle at the wall is infinite. Potential energy is, it can not move, right? Potential energy is maximum or infinite. It cannot move. That is the meaning. Due to the infinite potential energy outside the potential wall, particle cannot escape from the box. So the particle will be retained within the wall, within the structure, within the metal. The electron will be maintained within the metal. That is the case here, right? So on the whole, we can say Max Carl Ernst, Ludwig Planck, Albert Einstein, both of them contributed much more for our quantum mechanics, black body radiation, photoelectric effect, we discussed, right? In addition to them, Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Max Born, Paul Dirac, and others contributed in mid 1920s, right? So it started by Max Planck and Albert Einstein in 1900 and 1905, respectively. But in mid 20s, the rest of the people takes the torch of quantum physics. The modern theory is formulated in various specially developed mathematical formulas. In one of them, a mathematical entity called wave function provides information in the form of probability amplitudes about what measurements of particles' energy, momentum, and other physical properties. So we can say different torch bearers of quantum mechanics and their products as black body radiation, photoelectric effect, and different atomic models, and the work of Erwin Schrödinger, Heisenberg's uncertainty principle, right? We discussed so many things. And we must correlate quantum theory. The basics of quantum theory is supporting quantum computing. For that, this one, the Young's double slit experiment, we know, right? Likewise, here, quantum also having interference double slit experiment. So here we are taking laser source, and that laser, from the laser source, electrons are moving through the double slit and reaching the screen as interference pattern. So as a result of it, it would not be expected if light consisted of classical particle. The wave nature of light causes light waves passing through two slits to interfere, producing bright and dark bands on the screen. A result that would not be expected if light consisted of classical particles. However, the light is always found to be absorbed at the screen at discrete points as individual particles rather than waves. The interference pattern appears via the varying density of these particles hits on the screen. Furthermore, versions of experiments that include detectors at the slits find each detected photon passes through one slit and not through both the slits. However, such experiments demonstrate the particles don't form the interference patterns if one detects which slit they pass through. This behavior is known as wave-particle duality. So, in addition to light, electrons, atoms, and molecules are all found to exhibit the same dual behavior when fired towards double slit. So here also we are explaining dual nature, right? So we are moving towards conclusion. Now we are seeing quantum tunneling. So classical theory is saying it is impossible to cross a potential barrier, but quantum theory is saying that electron can move, that electron can travel through the potential barrier by tunneling, right? Particle goes up against the potential barrier, can cross it, even if its kinetic energy is smaller than the maximum of the potential. If its kinetic energy is smaller than the maximum of the potential, quantum tunneling is supporting for the penetration, for the transportation of electron from this region to that region. But in classical mechanics, this particle would be trapped. Quantum tunneling has several important consequences, enabling radioactive decay, nuclear fusion in stars, and applications such as STM, that is scanning tunneling microscopy, tunnel diode, and tunnel field effect transistor, right? Okay, so quantum tunneling also giving wonderful experience to quantum theory, right? Instead of moving and climbing over this peak, the quantum tunneling helps to move the electron through this tunnel. We can't travel unnecessarily beyond this potential energy. So quantum tunneling is one of the masterpiece of quantum theory. Here we can see the movement of the wave particles through tunneling. Okay. Classical mechanics says it is highly impossible. Quantum mechanics proves it is possible. So if E is greater than V, if E is less than V, quantum says it's possible. Okay. So finally, we are closing the relationship between quantum physics and quantum computing. Right. This is the starting point of quantum computing. Right? Quantum physics is the fundamental scientific theory describing the behavior of matter and energy at the atomic and subatomic levels. Quantum computing is an emerging technology that applies the principles of quantum mechanics, such as superposition. Superposition we observed in double slit experiment, and entanglement to create powerful computers that can solve specific problems far faster than classical computers. In essence, quantum physics provides the underlying principles and phenomena that quantum computing harnesses to perform calculations. Quantum for future technology, quantum communication, quantum sensing, quantum computing. The advantages we know: faster processing, complex problem solving, enhanced AI, and quantum supremacy. We know the superposition, right? And entanglement. If we are tossing a coin, we observe only head or tail, but in quantum computing, we can get the combination of both of them, right? Combination of head and tail, right? We can see this one only 0 or 1. But here in quantum computing, we are getting the combination of zeros and ones. This is superposition, right? Okay, so we can enjoy in future quantum computing as a result of our dual double slit experiment. So the seed given by our quantum physics or quantum mechanics. We are going to enjoy the fruits of quantum seed as quantum computing, quantum sensing. So with these things, and we are seeing two different wave patterns. At the same time, we are touching the
மெயில்ல இருக்கு. சார் விடுங்க, நான் பேசிக்கிறேன் விடுங்க. சார் சார் விடுங்க, நான் பேசிக்கிறேன். Sir Nicholas sir, are you joined on the line, sir?
Yes, madam. I'm on the line.
Yes, sir. Sir, you may give an introduction about sirs.
So today is our second.
Welcome, sir. So the second section is going to be presented by our distinguished resource person, Dr. S. Nicholas. So he is a director and professor from the Department of Computer Science Application at National Institute of Technology, Tiruchirappalli. So I'm very proud to be give an introduction about our today's resource person. So Dr. Nicholas is an eminent academician and research with over of 33 years of experience at NIT Trichy. So he's obtained his ME in computer science in 1992 and his PhD in data mining in 2007, both from NIT Trichy. And also he has had an interest of span some of the most cutting-edge areas in computer science, including machine learning and deep learning and data mining, big data analytics, and software metrics. So he has been a driving force in establishing advanced research facilities such as high-performance computing labs and big data analytics labs at NIT Trichy, and also served as a principal investigator of the CODE NVIDIA teaching centers. So in this career, Dr. Nicholas has held several important academic and administrative positions, including head of the department, chairman of MIS implementation, and have served on the board of governance of NITT. And he also contributed as a member of board of studies at leading universities, including Anna University, VIT, Pondicherry University, and VMMF. So his profile research contributes including over 90 publications in reputed national and international conference journals, and has guided numerous PhD scholars in frontier areas of computing. So his excellence has been recognized with a prestigious award such as a Distinguished Alumni Serving Faculty Award from MIT Trichy and Scroll of Honor from the Institute of Engineering India. So beyond his academic achievement, Dr. Nicholas is a passionate teacher, mentor, and investor who have inspired generation of students and researchers. So we are truly honored to have such a versatile and accomplished academician among us today. So on behalf of the organization, faculty, and student, we extend a warm welcome to our Dr. S. Nicholas, and we are looking forward to hear his inspiring address. Sir, welcome, sir.
Thanks, Professor, for the elaborate introduction. I am honored, and I am sharing my screen. Kindly inform me whether it is visible. Is it visible?
Yeah.
Yes, sir.
Okay, thanks. Let me start the session. Actually, the screen is moving.
Sir, it is only in the first slide, sir.
What's the problem? Is it moving, madam? Kindly inform me.
Sir, we are unable to see your screen, sir. Yes, sir, we are able to see the screen, sir.
thing is it able to move in?
No, sir. The slideshow is not visible.
What is the reason?
Not in a presentation view, sir. And now it is moving,
Yes,
sir. Make it a slideshow, sir.
that only I'm doing. Is it moving?
Yes, sir. If it is in third slide, sir.
Okay then. Thank
Now
you.
it is. Yes, yes, sir. Sir, kindly make
Okay.
it a slideshow, sir.
Yes, it is slideshow only. Is it moving or not?
It's moving, sir. Now it is in third slide, sir.
Okay, I'm going to the first slide only.
Yes, sir.
Okay. Good afternoon to all the faculty members of who organized this workshop and the participants for this session. First of all, let me sorry for my throat. My throat is not good. Kindly bear with me. So my topic is the basic introduction to quantum computing. And before going into the concept of quantum computing, let us indulge into the concept of our classical computers. So when you talk about our classical systems, basic building blocks of the classical computer that we have used, that is from the basic transistors to ICs and VLSIs, and nowadays we are talking about GPUs, etc. So the growth of the computer hardware is evolving in the years, and if you see, my agenda is this one anyway. If you see according to the Moore's law, the number of transistors that we are incorporating in a microprocessor chip is growing twice as much as every year, while the prices were reduced half since their invention. So this law talks about the growth that is happening in the hardware of the microprocessor chips. But the thing is that improvement in the classical computer is not like before it used to be. So this law cannot be applicable now, as we saw the drastic reduction in the price, but the growth happening in the classical computer. The size of the circuits of the classical computer after 5 to 7 nanometer has reached their limit. Maybe we can go up to the level of an atom. But the problem is these circuits cannot act as a switch as electrons inside an atom. So that is the thing. We cannot think about switches made of electrons which can work using the concept of electrons. So electrons, as we saw in the previous session through the quantum mechanics topic, which is wonderfully given by Professor Mani, so the electrons can exist in more than one place at the same time due to the teleporting phenomena in quantum mechanics, that is quantum tunneling. So this is one of the important phenomena by which we can claim that the electrons can simultaneously existing in multiple places. And before going there, we will talk about something about quantum tunneling. So the wave is a continuous disturbance that travels through the medium from one location to another, where the pulse is the single disturbance through the medium. So now quantum tunneling is an evanescent wave coupling effect that occurs in the quantum mechanics, where if you apply correct wavelength with the proper tunneling barrier, it is possible to pass the signals faster than the light. That is, we can overcome the barrier very fast in comparison with light. So completion of tasks exponentially faster than classical computer is possible because we can make the particles to simultaneously exist in multiple places, and also any barrier that is happening can be possible to overcome using this concept. So with this one we have already come across or practically using in our touch screens of the
Sir,
mobile
excuse me, sir.
devices. Yes, madam.
Sir, the slide is not changing, sir.
Why I don't know. Now, in which slide you are?
Third slide, sir.
I'm going to fourth slide actually.
But it is not changing, sir. Ah, yes, sir.
But it is not in the slide screen. So entire screen is visible to you, or
No, sir. The slideshow is not visible.
what's the problem?
Presentation view is not there, sir. No problem, sir. We may use that.
I'm sharing the entire screen only.
Yes.
Is it in screens?
Sir, your screen is shared, sir, but not as in the presentation view, sir.
Why?
You're not getting the full screen view, sir.
I'm sharing the entire screen.
Directly they can just move the slides there.
Okay, then I will move the screen. Okay. So, so is it in the fourth slide, madam?
Yes, sir.
Okay. Now is it moving?
Yes, sir, it is moving, sir. Now it is in fifth screen, sir. Fifth slide.
Okay. The
Quantum
problem is
tunneling photo.
mine is it's not going to the slide now. I have to log out and once again log it. Anyway, okay. So this concept is not a new. Already we are starting using in our screens of the mobile devices. Okay. So now, what is a quantum computer? So we know our classical computers are built upon the concept of the transistor as the basic building block. But quantum computers are the machines that perform calculations based on the laws of quantum mechanics, which is the behavior of particles at the subatomic levels. So we know at the subatomic level, we are talking about electrons, protons, and also photons. So uses quantum mechanical phenomena, basically the superposition and entanglement concept. We'll discuss more on these two concepts in the coming slides to perform the operations of the data. So when we are talking about I want to do some computation, the concept of the superposition entanglement being used to operate on the data. So in such small computers, circuits with transistors, logic gates, and integrated circuits are not possible. Hence, we are going to use the subatomic particles like protons, photons, and electrons as the bits along with the information of spins and states. So these two things are going to be applied for our basic operations. Anyway, you will be discussing more on these operations over this subatomic particles in the coming sessions. So normally in a digital computer, we are going to code our information in the form of string of bits, where each bit is either in the two classical states, that is 0 or 1, or either on or off state. But in quantum computers, the elements that carry the information are in the quantum states or quantum bits called as qubits. So quantum computing is the only model that could disobey the Church-Turing thesis, that is the computability theory, and thus quantum computers can perform exponentially faster than the classical computers. So what is this Church-Turing theory? According to Church-Turing thesis, the quantum computers can solve any computation problem that any classical computer can solve. But according to Turing thesis, the converse is also true. That is, classical computers can also solve all the problems solved by quantum computers. But the extra benefit over classical computer is that the complex and impossible problems that cannot be solved by today's conventional computer is in a practical amount of time can be solved by quantum computers. So as we saw in quantum mechanics, the concepts that cannot be defined using the classical physics can be explained using quantum mechanics. Similar to this, those problems that are highly impossible or taking more amount of time can be solvable using the quantum computers. So quantum computers are able to solve such problems in reasonably and exponentially lower time complexities, which is going to be called as quantum supremacy. So it is capable of solving any complex problems with less time interval, overcoming the drawback of complexity. Okay. And as an example, I can say in the healthcare industry, nowadays we are encoding the concept of machine learning, deep learning, so that the enormous computational requirements needed for this healthcare industry is possible because of the high usage of IoT and other devices, where we are taking more intensive care of the patients. But the other side, if you see the volume and the diversity of data that are being generated by these healthcare devices are going exponentially growing. So, for example, in during the COVID-19 period, we know the various variants of this virus emerge, and it is very challenging for the healthcare professionals to sequence the genome so that the virus can be identified, and computationally we can find solution for these problems. So this highlights the need to explore the ways to speed up our high-end computing systems to do healthcare analysis. So quantum computing thus provide us the facility to solve such complex tasks very fast. So that is the basic idea behind which we are talking about the quantum computer. So this is one example only. But when you talk about quantum computer can solve everything very fastly, it can solve the complex problems in very fast time. There is also another issue that we have to be taken care of. For example, Peter Shaw showed that quantum computer can solve complex problems considerably more efficiently without getting overheated. He developed algorithms for factoring large numbers quickly. But factoring a large number is one of the core concepts of cryptography. You know. So if you can break a cryptographic secret codes within a very fastly, then it enforces the risk of security over the encrypted data and communication and can expose private and protected secret. This is one of the major drawback or problem that you are going to face because of the ability of the quantum computer techniques to solve any problems that include breaking a complex secret key. So the advantage of quantum computers must also be kept in mind that it is significantly more than its flaws. So there may be some flaws happening, but you should also overcome such flaws when we evolve the concept of quantum computing. So to introduce the core, to enter into the world of quantum computers, we should discuss about the fundamental building block of the quantum computing called as quantum bits. So quantum computers, like classical computers, have two quantum states where it can be either a 0 or 1, but it follows the quantum property, that is the superposition, where it can have both the values simultaneously, which is one of the core concept by which we are talking about the quantum computer. So a quantum bit can simultaneously exist in both the states, that is 0 or 1. And the what if you try to measure whether it is a 0 or 1 at various position that the bit is occupying, then we can measure the value, and it can be either 0 or 1 based on the angle of measurement or the type of measurement you are doing. So quantum bit or qubit is the fundamental unit of quantum information that represents the subatomic particles like a computer's memory, while their control mechanisms work as the computer processor. So I can say that subatomic like an electron may be acting as the memory to store 0 or 1, and the control mechanism, that is like a photon by which we are applying the energy over the electrons as sort of computer processor. So as qubits are both digital as well as analog in nature, which gives the computer the computational power. So this is the basic thing. The bit can both, we can measure it as a digital value, or its value can be in analog in nature, by which we can do the computation over complex values of the bit qubit. So in classical computing, the basic building block, as you said earlier, it is a bit which can be either on or off. So every problem, regardless of its complexity in classical computer, we should be translating it to binary language, which can be understandable to a computer through the manipulation of its bit. But in quantum computing, the classical computer's bit is replaced with something that is capable of manifesting the quantum behaviors. First of all, that is the superposition between the 0 and 1 state called as qubit. Okay. So how the qubit is represented? A bit of data is represented by a single atom that is either in one of the two states denoted by ket 0 or ket 1. And this ket notation we will be discussing, bracket notation we will be seeing. The single bit of this form is known as the qubit, and the physical implementation of the qubit would use the two energy levels of the atom. So in the last session, you would have seen the quantum mechanics concepts, where the electron may be in the ground state or in the excited state. So an excited state representing ket 1 and a ground state representing ket 0 value. And qubit is defined as a ray in the Bloch sphere. That is the various a qubit can exist in multiple uh, levels or multiple states, and the block sphere is the mathematical object whose elements on the surface can be identified by the coordinates. So the x and these concepts we are not going in depth actually. So the psi value of the particle is measured by the two parameters, that is cos theta by 2 and ei phi sin theta by 2. So the poles of this pole block sphere represent the classical states 0 and 1, and without the loss of generality, the block sphere can be analyzed in the real world by ignoring the variable pi, effectively reducing the representation of the circumference. This is the basic mathematical model that can be used to characterize or compute the value of the qubits. Okay, so the Dirac or log bracket notation. Let us assume that sigma denotes the classical set of possible states, and assume the elements of sigma can be placed in the corresponding integers 1 to sigma, and get A, that is get 0 or 1, denote the column vector having 1 in the entry corresponding to A with 0 for all the. For example, if the classical state set is 0 or 1, get 1 0 can be represented as 1 0 column vector, and get 1 can be represented as 0 1, having 1 column 1 in the second. Another example, I can represent spade, diamond, heart, etc. Then is the possible states. Each state can be represented by having 1 in the particular place, but having 0 in all the other places. Okay. Now, the qubit representation, ket 0 can be represented as cos 0 by 2 and sin 0 by 2, which is 1 0, or ket 1 is cos pi by 1, pi by 2, sin pi by 2, which is 0 1. With this choice of coordinates, the classical states 0 and 1 represent a base value, and any psi value, that is the position of the particle or the current value of the particle, can be denoted by two amplitude values alpha and beta, which is cos theta by 2 and sin theta by 2. So the Dirac notation, where the row vector can also be used to represent the values, that is bra 0, that is what called a row vector 1 0, and bra 1, that is 0. So this bracket notation is used to represent the values of the qubit states, either row wise or column wise. So this computational part of this one, how it is used for generating the gates and application in this, depends upon the coming sessions we may be seeing. Now, coming to the quantum physical system, that is the it leverages the orientation of a photon or spin of an electron to create a qubit. So, in a quantum physical system, what we are talking is how to make an electron and using the orientation of the photon so that a qubit can be designed or defined. In come in one or two or higher qubit computers also possible. According to the literature, to reach the quantum supremacy, minimum 50 qubit is required, and recent IBM's quantum computing chip contains 432 qubits in Osprey and 1121 qubits in the current Condor computing chip. So this quantum physical system provides an environment where we can define how many qubits that you are going to have in your quantum computers, and what how this quantum computers is able to perform the various operations using the concept of qubit. So we have to define this terminology quantum supremacy in order to understand the ability of the quantum device to solve a problem which cannot be solved by a classical computer in a feasible amount of time. So three basic quantum properties are quantum superposition, quantum entanglement, and quantum interference. So from the quantum mechanics concept, we have seen these concepts in the earlier session. So let me talk about these quantum supremacy concepts based on the. So what do you mean by quantum superposition? The spinning electron question cannot be pinpointed to any specific location at any time. So what is the position in which electron is going to be? It is always in the movement. So we cannot identify or pinpoint any specific location. and we have to compute the value as a probability distribution in which the electron can exist at all locations at all times with varying probabilities. So this is the concept of superposition, where we are assuming that the electron is available at all locations, and the cubic group of qubits used for calculations can be either 0 or 1 or a linear combination of both of these. So these linear combinations are termed as superposition. So in order to understand the value of the qubit or measure the value of the qubit, even though they are occurring at all locations, we can apply a linear combination equation so to find the value. These linear combinations are termed as the superposition state. So qubit can exist in two states. So a quantum computer with n qubits can be in arbitrary superposition of 2 per power n, 2 power n different states. This speaks about the uh, advantage or facility we are having, so that by having some 2 or 3 qubits, we can make the system to exist in different states, different possible values. That is the advantage that we are going. For example, in the binary computer system, if I have a single bit, I can have it can be either in 1 or 0 state. If I have two bits, it can be either in 0, 0 or 0, 1, any one of the 4 states, but not at all the 4 states simultaneously. But when we talk about qubit, if I have some 2 qubits, I can assume that due to the concept of this superposition, all the 4 different states are simultaneously existing, and the computer can do work on these 4 states simultaneously. So the representation of data in superposition is a single qubit can be forced into superposition of the two states denoted by the addition of the two vectors alpha 1 get 0, alpha 2 get 1, where alpha and beta alpha 2 are the complex numbers whose square summation is equal to 1. So this can be used to compute what is the current position. Say a qubit in superposition in both the states get 1 and get 0 at the same time, but you can compute the value based upon this equation where psi is equal to alpha 1 get 0 alpha 1. So the representation of data in superposition is by applying some light pulse, we can make the state 0 to be superposition on gate 1, and so the simultaneously both the electron is existing in both the 0 and 1 state. This is called as the superposition state, and depending upon the probability value assigned to this position value, we can assume that or find the value of the qubit and that particular term. Now, in mathematical terms, the superposition state can be manifested by a qubit is expressed as a linear combination of the classical state 0 and 1. So psi is equal to alpha beta, where which is nothing but the cos theta sin theta value. So chi of alpha 1 comma 0, that is the ket 0 plus beta ket 1 is equal to alpha ket 0 and alpha ket 1. So by using this equation, we can compute what is the current value of the qubit. So alpha and beta are the commonly called as amplitudes, and they are the probability of observing a qubit in one of the corresponding state. So by using this equation, we can compute what will be the value of ket 0 or ket 1 using depending upon the position of the value chi. And the example for we can how to understand this, we can see a puzzle like maze. A quantum particle can decide to take various paths at the same time using superposition. That is the idea of basic advantage. So if I want to solve a problem, or in the case of chess problem also, I can assume that we can simultaneously make a move in all possible directions, so that we can analyze which is the best path and we can make a move based on the all possible analysis. So due to this property, the qubit is able to navigate the maze in exponentially less time than a classical bit, where we can move one at a time only practically possible. So measuring the qubit, as I said, the chi-square psi value can be computed using this. Even if it can be represented mathematically, it will be never possible to observe a state of superposition. So quantum computing involves the measurement operation with the aims to make the known value of certain qubit orbit. So the fundamental difference is that the measurement of a qubit destroys the superposition state, even if it is in multiple states, it destroys it and forces the qubit to assume any one of the state that is going to be called as the collapse of the qubit. So this is the basic idea behind which they are going to. So the qubit can exist at simultaneously at different positions using which you can combine or do manipulations. But when you try to measure the value, at the end it is going to be giving the single value. That so this concept is the core idea by which we are claiming that the quantum computing is able to solve the problems very fast. So in a simple term, or in a what I can say, we can take this as an example. In the deep learning nowadays, we want to or in machine learning, we want to, for a feature, for a attribute, which can take multiple values, we want to find a class label for this attribute, or multiple features are there in a class table for which we want to find a class table. We have to formulate rules or build a tree analyzing each row separately one by one, so that what are all the possible values each row is taking. Based on that, we want to make a class label. But in terms of quantum computing, if you see this problem, simultaneously each attribute can exist in multiple take and occupy multiple values, and I can collapse this into multiple attributes, and I can find the class label within a single unit of time. That is the advantage. So this is some crude example only I am telling, but the advantage we can understand that. So instead, even if I have multiple states for a single feature or multiple values for a single feature, I can find the class label simultaneously by browsing all the features with various combinations. This sort of things are possible only in terms of quantum computers. And so the probability of I equal to 0 or 1 is the equal probability, because if it depends upon the collapsing value, how what time interval at which we are going to collapse the thing, and based on that its value is going to be computed. So if theta is pi by 2, the chance for the bit qubit becoming get 0 or get 1 depends upon the which is having the equal probability. Similarly, if the theta value is 3 pi by 2, the same probability, equal probability is existing for these two things. Now, the second concept regarding quantum supremacy is the quantum entanglement. So, it is a physical phenomena where two or more quantum objects are inherently linked such that the measurement of one rule the possible measurement of other. This is one of the important advantages. That is, assume that I am having two qubits and they are inherently linked. So, if I try to measure the value of one qubit, automatically it is possible for us to simultaneously measure the value of the other. So this is based upon the concept of intertwined pair of systems. So knowledge of anyone immediately provides the information about the other, regardless of the distance between them. So whatever be the distance, whatever be the duration or barrier that is coming across them, this entanglement is the ability of the quantum systems to exhibit correlations between the states within a super. So, in physics, when two systems such as photons or electrons are highly interlinked, so that the one state immediately provides the information about the other state. This is one of the another important property of the quantum computers. So, modifying one tangent qubit state immediately perturbs the paired qubit state, leading to instant communication and increased conflict. So, as I said in the concept of machine learning, if these quantums, each qubit is talking about one feature, the measurement of one qubit or the modification of one qubit, which is talking about one attribute, will immediately made us to measure the other attribute value. This plays a vital role in the quantum computers to work. So quantum entanglement is necessary for exponentially faster performance of the quantum algorithm. So by measuring the value of one qubit, I can measure the value of other bits. This entanglement helps me to find the value of other qubits very fastly or instantaneously. And state of one particle influences the state of the others and creates a strong communication between the qubits. So once the particles got the objects got entangled, they will stay connected even after separating that distance. But in classical computers, if the bits are doubled, computational power also gets doubled. But in the case of entanglement, adding extra bits to the computer can increasing the computational power exponentially. So this is the difference between the two. So if I have a 4-bit computer increasing it to an 8-bit computer, only the computation power may be doubled. But in the case of entanglement, if you add one more extra bits, it exponentially increases the computational power. And so electron separated from each other at some distance inside an electron cloud are massively entangled with one another. And this is an example of nature. And the third property is the quantum interference. That is, the particles, we know the particles we are talking about, subatomic particles, have some wave-like properties, and these wave-like properties are attributed to the location, for example, an electron around a nucleus. So this uh, wave-like properties in two phase waves peak at, if two in phase waves peak at the same time, then they are called as constructive interference. That is, if I have two waves, separate waves, two, then if you have them interfere at the same time or they peak at the same time, then it is going to be called as constructive interference, resulting in waves peaking twice as high. Whereas destructive interference is also possible where if they are out of sync, and then the interference is going to be called as destructive interference. So all the other, if I have interference at different various other levels, then it will be resulting in a higher peak for constructive interference or a lower peak for destructive interference. So this interference is used to affect the probability amplitudes when measuring the energy levels of a qubit. So this interference is going to affect the probability amplitudes that alpha and beta or alpha 0 and alpha 1 we talked here. So now these three properties, that is quantum superposition, entanglement and interference, talks about the quantum supremacy, by which we are claiming that the quantum computers are having the complexity power to solve any complex problems, and they are computationally effective or efficient. These are all the three. Now, what is the difference between a classical computer and a quantum computer? On the basis of the computing, we can say LSI circuits can have a multi-purpose computer based on classical physics, whereas the quantum computers are high-speed parallel computer based on the quantum mechanical concept. And the storage unit is a bit, whereas here the storage unit is a quantum bit, which is based on using the electron spin. And the bit values are either 0 or 1, whereas the case of qubits having a value of 0 or 1, or sometimes can have both the values at the same time. And the number of possible states is 2, which is either 0 or 1, whereas the number of possible state is infinite, which can hold combinations of 0 or 1 along with some complex information. This is the whole gadget. And the output you are expecting from the classical computer is deterministic, whereas the output that we can expect from a quantum computer is a probabilistic, because the repetition of the same computation on superposed states gives probabilistic answer. We cannot expect the same probabilistic value because of the superposed state. And the gates used for processing is the logic gates like AND or NOT, whereas the quantum logic gate processes the information in parallel. Anyway, we will be discussing these things in the coming sessions. And scope of the possible solution is defined and limited answers only, whereas this is a probabilistic and multiple answers are considered due to the superposition table. And the operations are Boolean algebra operations, whereas the quantum computer operations are linear algebra and are represented with integral matrices. And the circuit implementation is we are implementing based on the macroscopic technology, that is in terms of transistors or CMOS technology we are talking, whereas the circuits are implemented at the microscopic level based on the nuclear magnetic resonance that are slow and delicate. Okay. So the coming to the architecture, the we are not going to delve in depth about these things. Only it is a combination of classical and quantum parts consisting of 5 layers. That is the application layer, which is not a part of the quantum computer. It is not. It is a classical computer part only. used for representing a user interface, the operating system for quantum computer, coding environment that are needed for formulating the quantum computer algorithms, and it is hardware independent. So this is the topmost layer, which is used mainly for communicating with the user and the in inside quantum computer. The second layer is the classical layer. It optimizes and compiles the quantum algorithm into micro instructions. So the computer algorithm, quantum algorithm that you are developing will be converted into micro instructions, and it processes the quantum state measurement written back from the hardware in the below layers and gives it a classical algorithm to produce the results. So this is like the block diagram of a digital computer. We're talking about the classical quantum computer block. The third layer is the digital layer, which interprets the micro instructions into signals or pulses needed by qubit, and it acts as the quantum logic gates, and the digital description of the required analog pulses in the below layers. Also, it gives the quantum measurement as feedback to the above classical layer. And the next layer is the analog layer, which creates the voltage signals which are having a phase and amplitude modulations like in wave for sending it to the below layer so that the qubit operations can be executed. So the necessary signals for the proper execution of the qubit operations are being carried out in this layer. The final layer is the quantum layer, which integrates with the digital and analog processing layer onto the same chip. It is used for holding the qubits, and it is also able to handle the error correction and determines how will the computer. So this is the bottommost layer on which we are talking about the capability of the computer, that a qubit, number of qubits it can handle, and number of qubits it can be used to manipulate the given problem. So there are different types of quantum computer possible which are working mainly on analog or it's also digital. So analog quantum computing, it is energy environment representing Hamiltonian, is frequently changed smoothly as qubit operations. So they are built along analog in nature, and it changes smoothly into the 0 or 1 or digital notation. It initializes the quantum state, and this uses the Hamiltonian directly to develop the quantum state. So this analog quantum computer includes the concepts of quantum annealing, quantum simulation, and adiabatic quantum computers. So what do you mean by quantum annealing? It is the basic rule in physics that everything inclined towards the minimum energy state of a problem. This behavior is also true in the world of quantum physics. So quantum annealing is used for real low energy solutions such as optimization problems. So done in using some initial set of qubits that gradually changes the energy encountered by the system until the problem parameters are defined by Hamilton. So useful where the best solution is needed out of all possible solutions. So this concept is basically used for solving the optimization problems. For example, algorithm to optimize traffic flows can be applying the concept of quantum annealing. And quantum simulation is useful in using for chemical reactions to study the chemical reactions on a large number of quantum subatomic particles. Quantum simulators can be used to simulate the misfolded protein structure. Diseases like Alzheimer's are caused by misfolded proteins. So, examining such problems in quantum mechanics that are beyond classical physics. So, simulating quantum phenomena that are complex in nature is one of the important aspects of quantum simulation. And diabetic quantum computing is the dominant one, which is applicable and hardest to create. And this one is used over a million qubits. The maximum qubits we can access is less than some 128 today. The basic idea is that the machine can be directed at any complex calculation and immediate solution. So these are all the different forms of quantum analog quantum computing that we are trying to achieve. Then the digital gate-based quantum computing is similar to the classical computer approach. The problem is decomposed in a sequence of fundamental operations or gates, and gates have adequately defined digital outcomes for some input stage. The set of fundamental operations of quantum computing is different that of the classical computing. So the NISQ stands for the noise intermediate scale quantum, and it is the digital NISQ. So these two different varieties of quantum computing can be used for different types of problems that we are facing. Now coming to the advantages, when you talk about what are the need or advantages, as we discussed earlier, it can be useful for solving complex mathematical problems which the traditional computers cannot be able to solve in a particular time frame. And it provides a computer power which are sufficiently excessively large amounts of data because of the enormous amount of data nowadays we are generating. It is very very difficult for the classical computer to execute this amount of data, and this quantum computing provides such enormous computing power which can process this huge amount of data in no interval of time. And due to the teleportation problem known as quantum tunneling, we can work with parallel and less amount of electricity. So this is another important advantage. We can reduce the power consumption up to 100 to 1000 times by using this concept. And the optimization problem, we know finding a solution for optimization involves searching a huge amount of search space. And whatever solution we are finding using the heuristic algorithms or the meta heuristic algorithms, they can only find the near optimal solutions because the number of combinations that can be searched through the search space is very minimal. Whereas if you use these quantum computers, simultaneously we can probe the very possible search space locations and we can evolve the answer. So the solution of this optimization process is going to be very easily solvable, and also we can compute all the possible solutions and best solutions can be achieved. And also, it is possible for us to crack the highest security encoders, now, which nowadays it is unbreakable encryption techniques can be breakable. But this also gives an avenue for us to build a hack-proof alternatives in our encryption methods. Whereas coming to the disadvantages, due to the advancements of QC, the security of the existing IoT would fall down. As I said earlier, it is very easily hackable, and so the quantum computers can be terrible for our future. It is going to be one of the major problems that we are going to face. And quantum computer work as a different device, and it cannot replace a classical computers entirely because the it is practically viability and availability to every user is one of the very difficult important thing. And the entire device architecture is completely different, and as similar to a laptop device, whether it is available to every user is which is not practically possible nowadays. And it cannot not been invented completely yet, as only we are talking about here some parts are being implemented and people are still imagining how it would look, and very delicate and error prone. This is another important thing. Any kind of vibrations affects the subparticle like atoms and electrons, due to which the noise, faults, and even failures are possible, leading to decoherence. So our output is always disturbed by the noise, enormous amount of noise that we are going to face in this subatomic level. So quantum processes are very unstable and are very hard to test. So for the stability of the quantum computer, the temperature at which you are to keep the machine is going to be very zero point 0.2 Kelvin nearly, which is not possible for every uh, place or every installed at every place. That is one of the major. Coming to the applications, I can talk about many quantum algorithms have been evolved for quantum computers, but they deliver speed up, which is the result of some fundamental mathematical methods like Fourier transform, Hamiltonian simulation. But most algorithms requires a large number of qubits. These algorithms are formed in blocks rather than as a whole. So they're talking about, as I said earlier, implementation is in the parts wise only, not as a whole is not possible. Therefore, it is a great challenge to create a quantum application that are really practically useful along with speed up at the no error. And for example, we can apply quantum computing in cryptography, but uh, as we know, the breaking uh, RSA technique in which we are talking about breaking a huge prime numbers, which is not practically possible in classical computers. And also modern algorithms like AES, CSDC, etc. cannot be cracked using even high computing power. But when you talk about quantum computers, can do all these kinds of stuff in exponential less amount of time, And because of this, new encryption techniques are to be made to resist the quantum loss. This is one. And when you talk about optimization problems, as it is very possible, very easy to find an optimal solution, and with minimal error and minimizing the steps available. So quantum computers are best in solving optimization problems, and there are a lot of quantum algorithms out of which quantum optimization algorithms might improve the already existing optimization problems. So simulating the molecular model like protein behavior for medical research can lead to a new discovery of drugs for serious diseases like cancer and lung. So healthcare applications, when you talk about the applicability of quantum computing, it is enormous in nature. And coming to our AI, as we know, the use of deep learning and machine learning algorithms in different domains of problem solving. It is now talking about AI. There are large amount of data sets that are to be used for our learning, inferring, and understanding. So, but the quantum computer makes it easy and accurate. And conventional computers are only training the learning model, whereas quantum computers can train these models over a huge data set without sticking to the time, exponential time. And the generative models we are talking about nowadays using image, audio, etc., can be fed to the quantum computers to improve its quality and accuracy. And NLP can is another area where we can apply the quantum computers. So quantum computers can make it understand all the phrases and speech in real time with improved quality, which is computationally costly in today's classical computing systems. And as he said, healthcare is one of the important domain where we can apply quantum computing in terms of precision medicine. So identifying and explaining the relationship among the causes and treatments, predicting the next course of action at individual level. This is the important goal of precision medicine. So based on the causes and the treatments that are be ongoing for a patient, we can predict what type of next course of action immediately we can. So quantum computing enabled diagnosis utilize the continuous data streams using the personalized interventions in predicting the disease and prescribing the relevant treatments, optimizing the predictive machine and personalized healthcare services. So these are the example where many input factors are given to the quantum computing model, by which we can go for granular understanding of the healthcare status of the patient, and we can go for precise medicines that can be given to the patient. So, and in drug research also, we can go up for using the quantum computing, possible to encode the tens of thousands of proteins and simulate the interaction with the proteins. But though there are so many advantages and applications possible, there exist a lot of challenges and opportunities in terms of quantum computing. The thing is, decoherence is one of the important challenges. That is, qubits cannot naturally ignore the noise. So the quantum system is more error prone and it suffers from decoherence. So classical computers can produce a clean noise-free outcomes by simply putting its states as off or zero, which is not possible for quantum computers. Because even when an error occurs, there will be possibility of the state being in an oscillation. Qubits will gradually lose its information as well as interconnection between each other. So the error rate is seen as as a design parameter for such systems, which should be improved in large qubit systems. However, to make the qubit stable or error-free, they are being insulated from the outside environment in super refrigerated fridges and vacuum chambers and accurately handled. So this is one of the important property problem decoherence that is to be. And error correction, as I said, qubits are neither completely binary nor digital, and it is having analog properties also. So gate can reject noise by dealing the input signal with value zero point 0.8 and treating it as 1. So even though the noise level is zero point 0.2, it can consider it as 1, but in the analog signal, every value between 0 and 1 is permitted since they are having their mean. So signals cannot be checked for any kind of noise or corruption. So any noise happening in the bit position cannot be measured properly, and presuming the error as zero like gates do, or taking some noise value even if it was not present, that can affect the resulting quantum computation. Hence, there is a need for algorithms in to have quantum error correction similar to the logical error correction in quantum. So, which is one of the major problem in the case of quantum computing. And other challenges include quantum algorithm development. Specific algorithms are needed to be built upon for replacing the features or advantages of the quantum computing. And debugging is another issue. So the debug depends on the memory and intermediate machine states in classical. So when you talk about debugging, what is the intermediate? Run time decoding is possible in the case of classical computers, but in the case of quantum computing, states cannot be copied directly because the measuring the intermediate state at a different time interval will give different result. So new strategies for debugging are essential for the development of quantum computing. And security and quantum cryptography are required because the capability of quantum computing can break the any secret codes or encoded value. So we have to talk about quantum cryptography so that this problem can be rectified. And quantum communication networking is a complex challenge. Developing a quantum repeaters to transfer the information to over a long distance communication protocol is suited for large scale quantum networking. And also power requirements is another important issue that are to be. So the requirements of any quantum computer, they talk about the computational power, high speed connectivity, high dimensionality, scalability, quantum availability. So these are all the major requirements that are needed for a quantum computing environment, which also talks about the opportunities. So the necessities or requirements of quantum computing talk about the opportunities that are possible in terms of the component level or the deployment mode, technological level, like application level and the end user level. So there are so many opportunities possible. We talk about the quantum computing and the current growth when you talk about quantum computers. IBM is doing enormous amount of research on this, and as I said earlier, the chips they are more than 1,000 qubits in a quantum computing they are having, and currently allows access to its machines to the researcher organization, universities, laboratories. And Microsoft also offering companies to access the quantum technologies via Azure Quantum. So, so quantum computers is coming into the real life usage and applicability, and all our algorithms in terms of classical computers are to be updated or upgraded to quantum computing algorithms, and all our cryptographic techniques that are built upon the classical environment should also. So there are a lot of opportunities that are available or possible by the advent of these quantum computers. So thus, uh, with this, I will stop my session on a brief introduction about the quantum computers and its advantages and its applicability. Okay, madam. So with this, I stop my introductory lecture. Thank, thank you.
Thank you, sir. Thanks for your valuable effort. My heartfelt thanks for helping me grasp the basics of quantum mechanics, needs, issues, developments, etc. Your clear explanation and the patient guidance made me such a complex subject feel much more approachable and fascinating, sir. I truly appreciate the time and effort you took to share your knowledge. It's made real difference in my learning journey, sir. Thank you so much, sir.
Thank you very much, madam. Thank you.
Thank you, sir. Sir, the participants are requested to fill the feedback form as well as the attendance form, which was displayed in the chat box. If you are not able to get it now, we'll post it in the WhatsApp group also, sir. Kolu sir, thank you so much, sir.
Okay, madam. Can I leave? Yeah.
Yes, sir. Yes, sir. Yes, sir.
Thank you.
Thank you so much, sir. Participants are requested to fill the feedback form as well as the attendance, which was given in the chat box. If you are unable to open the link, please call us or else open the WhatsApp page, which was given in the WhatsApp group itself. Audience, you have any questions, please post your questions in the chat box itself. We'll post through the respective resource persons. Dear professors, you had any doubt on the previous 2 sessions, you may post your questions in chat box itself. எனக்கு வாட்ஸ்அப் லிங்க் அனுப்பிச்சுடுங்க.